Hello students, so today we'll go for the last video of this chapter of IR spectroscopy. Okay, so today we'll go for the instrumentation of this IR spectroscopy. Okay, so if you see the principle of this spectroscopy, that it is based on the principle of interferogram. Okay, interferogram interferogram. Okay, and the and it's also called as interferometry. Okay, interferometry, and we get interferogram from this spectrometer is obtained, and this is a very complex type of signals. Okay, very complex signal is obtained here from this interferometry, and this occurs in the form of waves. Okay, it occurs in the form of wave like pattern. Okay, and and in this here the interferogram is plotted versus if you see intensity. Okay, it's plotted this interferogram is plotted versus intensity. Okay, plotted versus this interferogram is plotted versus intensity versus plotted intensity versus time, so this is how the interferogram can be shown for FTIR. Okay, now if you see the diagram representation of this FTIRs, I have taken here the diagrammatic presentation here. So you can see this is a diagram of the FTIR. Okay, FTIR, Fourier transfer information. So you can see here, so it is having a source here. Okay, radiation source here. So usually it is used as source is been used for the this is the it is that's called nursed glower. Okay, nursed nursed glower. Okay, GLOVR glower, or sometimes they use globar. This is a source is used which will emit a long range IR radiations, and this IR radiations is passed through the splitter. This is called as beam splitter. Okay, so this is a beam splitter. Okay, which is placed at around 45 degree. Okay, and you can see here there is a mirror here. This is stationary mirror, and you can see here this is a movable mirror here. So this is a movable mirror, and these are the different mirror. This is what the specialty of the FTIR. In IR, this all thing will not be there. This deflecting and non-deflecting, this all thing not be there in the IR. It's a simple. But in FTIR, you can see that there are different mirrors at a different positions here. So delta is equal to 0, then lambda by 2. This is a fraction. Then again integer delta which equal to lambda. Then delta is equal to 3 lambda, 3 by 2 lambda. Again integer, non-integer, like this. So these are different mirrors. They are rotating. Okay, and because of this all things, you can see that the absorption of the in all angle, the absorption of the radiation is been absorbed by the sample here. And this is what now what happens here, the radiation is passed through here, and you can see here it is falling on to this mirror here, so which are having different orientations, and it is coming back here. Some is non-deflected. Okay, some is non-deflected and come back, and some of the radiations they deflect here. So this mirror radiation, you can see they are deflecting here, and even there is a stationary mirror here. So some of them are going here like this, they hit here and again they come back here like this. That means you can see that the sample is absorbing both radiations, the radiations from the movable mirror as well as the radiations from the stationary level, and non-deflected also we can see here. So these are the deflected like this. Okay, and these are the non-deflected. So this is what the procedure taken place in FTIR. Okay, and the sample is been absorbing the radiations with respect to its vibrational frequency, rotational frequency. Okay, we have learned this in the previous videos, and this has been detected by the detector. Okay, and you can see here the detector will give you this interferogram in the form of waves. This is what very complicated here. So we are going to get in the form of waves here, and you can see that it is been transformed into computer where mathematical programs. Okay, so where mathematical program is been or formula is been applied applied here, so through software, and you can see that you are going to get the recorder, the final what do you say, the um, final spectrograph here. Okay, so intensity versus time. So this is what we are going to observe. This is how the overall diagram of or presentation of the Fourier transform spectroscopy is can be presented. Okay, flow diagram. Now if you go for each and every points here, so if you go for the now radiations, okay, so radiation, so we can see that it is nothing but the nurst glower, okay, NERNST, nurst glower or global eye radiations. Okay, so then the beam splitter, so that is what we can see that the beam splitter is also there, and the advantage of this nurst globar is that it emits the eye radiation or wide range of okay, wide range of wavelength. So this is what, so this nurst globar is emitting the eye radiations or the wide range of the wavelengths. Okay, and similarly if sometimes globar radiations, so globar is there, they also using the FTIR, and this is nothing but the rod. Okay, it is nothing but a rod like a sintered silicon carbide, made up of sintered silicon carbide. So this is what about the globar. Okay, and it is having around 5 centimeter, okay, length, okay, 5 centimeter length, and around 4 nanometer width of width, 4 nm width. Okay, so millimeter width, mm width. So this is what about the globar source. Okay, and it works at a temperature of 1300 degree centigrade, 1300 degree centigrade. And you see the splitter here, so splitter also same thing here, two types will be present, prism as well as gratings. Okay, as well as gratings. This is what, okay, prism is in the IR, we can see simple in the IR, but gratings we can see in FTIR, where you can see that different, this is all the gratings, different mirrors. Okay, series of parallel straight lines cut off the plane surfaces we can see here. Okay, so this is what, and even the detectors we can see of photo detectors or sometimes thermal detectors will be there, thermal detectors or photo detectors. Okay, they have been used, and if you see the frequency, okay, so it has been working in 3 frequencies, that is near IR. So you know that is work under the frequency of 1200 to 4000 per centimeter. Okay, this is what about the near IR. Then the main IR which interested is around from 4000 to 625 per centimeter, 4000 to 625 far IR. So in far area, it's we can see that it's on the 625 to 10 per centimeter. Okay, so this is what the range this near IR and far IR is working on this. You can see that they are going to work. Okay, now if you see the what you say the instrumentation here, how this is helping us. Okay, so these different angles you can see integers and non-integers. Okay, so it is useful for driving the very complicated form of the interferogram. Okay, so whatever the radiations is deflected, is been deflected from this beam splitter here, so they will be, as I said, undeflected and deflected, and they are positioned at a angle of 45 degree. Okay, 45 degree. So it's a very important here, so slightly in this way it has been like this, it's been 45 degree, and so that the radiations is been splitted upward and coming here, and all the ways the radiations are been absorbed by the sample here. So very nice absorption is going to take place with all the vibrations and rotations frequency. A clear picture is going to get from this FTIR, but the same thing we lack in the IR spectroscopy. So that's why this is one advantage of the FTIR. Okay, so maximum absorption, no, not a single left over. So because of this all designing of these different mirrors here, so this is what here. And if you see here, absorption radiations, and these are transmitted radiations, and they are passing through the sample here. Okay, and the detector will detect the radiations. So and it will give the interferogram. So this is what, and this detector will detect and it gives the interferogram, and this is processed by the computer here, processed by the computer through Fourier transform, and we get the spectra of the spectra of this Fourier transform spectroscopy. And during which, how does this happens here is because of this. So what we are getting from here is the in this we are going to get in this way. So I will do here, so like this, and this is what we are going to get here in this way, like this. Okay, because of this all mirrors, so we are going to get in a waveform initially in interferogram. So where we call this upper as a constructive, so this part upper is, we call it as a constructive. Okay, this is called constructive and destructive. This we call it as a destructive, we call it as a destructive. And why, when this comes constructive, this constructive comes when delta is an integer multiple, like this, integer multiple of lambda. Okay, so like this, like this integer multiple of lambda. So when this is there, integer multiple of lambda, so when this type of arrangement is there, so we are going to get constructive. And when we get the destructive here, so when the signal, this signal is occurring when the delta is the integral multiple of fractional integral half multiple fractional multiple of the lambda here, so like this. So 3 by lambda by 2, lambda by 2, like this. So fractional when we got the destructal type of views. So like this, constructive views and destructive waves is got from the different different orientations of this mirror. And totally we will get the overall absorption of the sample here. And finally it has been transformed, that's called Fourier transformed here by the computerized system. And finally we get the normal spectra here in this way, as we see. So this is what here. Okay, and the Fourier transform equation, okay, it's a computerized equation. It is given by the formula. So y is equal to summation infinity, okay, so n is equal to 0, a n sine of sine a n sine of n omega x plus bn cos, okay, bn cos n omega x. So I have taken very short ways, final mathematical derivation of how the Fourier transform equation is been formalized in the computerized here. So the summation of both here, ax sine n omega x and b naught plus b n b naught n cos n omega x. So what is this omega? So omega is given by the formula 2 pi by x2 minus x1, x2 minus x1, this is your omega. Okay, 2 pi by x2 minus x1. So these are the scale, okay, scale of x-axis, where x2 and x1 are the scale of the x-axis, which determine the resolution. So because we know that the wave number is nothing but 1 by lambda. Okay, so this is what we have to see in terms of wave number. And if you see the scale of the x-axis and here, so if we go for how this omega value is going to help us, so you take it to x2 and here x1 or x2 here, x1 x2, so you get like this. Okay, something like this. So this will be a very weak resolution when x2 is less here. So when x2 is less than this one, so we get a weak resolution. And if x2 is more, so if we go for little bit high x2 here, x1 x2, okay, so when you go for little hard, so we get a little bit better resolution here. And again if we go the x2 x1 very this one, so we get very nice resolution, again better resolution. So this is very better resolution, like this. Okay, so that is what more the x2 value, so better will be the suppression or the spectra here. So like this. So this is how from the omega, so we can see that the spectral differs here. And this is how I think the principle as well as the working nature, okay, as well as the systematic diagram of this FTIR can be presented. Now if you go for the what you say advantage, okay, if you take the advantage of this, so this signal to noise ratio, if you see the signal to noise ratio of FTIR is very low as compared to the IR. Okay, so better resolution is been observed in this FTIR. So this is first you can say the advantage of FTIR. And if you see the second, that it gives multiple scan. Okay, so there is a multiple scan is possible from this because of the mirror positioned. So definitely we will see that the better accuracy as compared to IR spectroscopy is observed for this FTIR. IR. So this is what about the advantage of the FTIR. Okay, so hope you understood this instrumentation of the FTIR and its different parts and the graphical presentation. Okay, and finally the advantage. Okay, so here we completed totally 100% of unit 4. Okay, and here it also completes your 100% portion with respect to inorganic. Okay, and probably by I think you have completed, one batch has completed 100% practical also. Okay, one batch. So this is how so we'll end here, and if any doubts or if we get any questions on the CSR net competitive examination, so surely we'll go for the video or the online offline classes as going on for studying the different concepts of this in a competitive way. Thank you.